welcome to this explainer. Look, if you're tackling the Cambridge 0625 syllabus, you already know that physics can sometimes feel like this giant, intimidating wall of disconnected formulas. Just a massive list to memorize, right? Well, today, we're going to completely break that wall down. Think of your exam preparation like training for a marathon. You have to pace yourself and really manage your energy. And you do that by moving beyond rote memorization. We are going to completely master the core cause and effect physics behind measuring volume and density. So, by the end of our time together, you won't just be regurgitating formulas. You're going to understand exactly how to build a perfect exam answer right from first principles.
Okay, so here's our roadmap for today. We'll kick things off with a core starter question, then break down the four-step DREA method. After that, we'll master cause and effect reasoning, look at some pretty cool real-world applications, learn how to dodge those super common exam traps, and finally, secure it all with some quick recall strategies.
All right, let's jump straight into Section 1, the starter question, making physics necessary. We really need to make the math feel absolutely vital, rather than just, decorative window dressing before we touch any equations.
So, before we even glance at a formula on the whiteboard, I want you to always stop and ask yourself, what physical effects, measurement, or prediction actually depends on understanding volume and density? Seriously, why does this even matter? Because if you start with a concrete necessity, like, say, figuring out whether a newly engineered cargo ship is actually going to float, or exactly how much fuel a transport system can safely hold, you instantly ground the physics in reality. You're not just pushing random numbers around on a page anymore, you're solving a tangible, physical problem.
And this quote right here, it really hits the nail on the head. Starting with that concrete necessity is just vital. When the core idea actually feels necessary to you, you become so much less dependent on memorized wording. We've all been there, right? You memorize a textbook definition of density, but the second the exam question phrases a scenario in a slightly weird or unfamiliar way, your brain just completely freezes. But if you start by understanding the necessity of the concept, you can logically reason your way through those tricky, unfamiliar questions with total confidence.
Moving right along to Section 2, the four-step TRIA method, your core framework. If you want to consistently hit those top marks, you absolutely need a reliable system to structure your answers.
So, what exactly is DREA? Well, it's a sequence of 4 linked steps, and it is exactly how you should be tackling any structured exam question. First up, D for definition. You have to clearly identify the quantity or phenomenon you're dealing with. Second, R for relationship. State the relationship involved, and yes, this is where your formulas finally come into play. Third, E for explanation. Explain the underlying physics of why this is actually happening. And finally, A for application. Connect all of that back to a real observation, experiment, or device. Following this sequence guarantees your answers demonstrate deep understanding alongside practical application. Honestly, this DREA method is quite literally the safest exam structure you can use to protect your grades. Think of it as your exam armor. In IGCSE-style physics, the examiners are actively hunting for answers that show both a theoretical grasp and practical application. By consciously checking off definition, relationship, explanation, and application in your head as you write, you are actively protecting yourself from dropping easy marks on those really high-value structured questions.
Let's look at Section 3, mastering cause and effect from language to vocabulary. You can't just skip straight to the end of a physics problem. There's a really natural progression to learning how to speak like a true physicist. A huge mistake a lot of students make is jumping the gun. You should always move gradually from everyday language to a concrete example before you ever rely on a symbolic physics equation. Let's think about volume and density. Start with a common everyday phrase like, "Oh, that's heavy for its size." Then move to a concrete example. Okay, a block of lead feels way heavier than a block of wood of the exact same size. Only when that concept is completely locked in your mind should you bring in the symbolic relationship, the equation itself. Actually, skipping straight to the symbols, that is exactly where the confusion usually starts.
And hey, this cause and effect reasoning extends directly to how you handle your data, too. A slope on a graph isn't just rise over run. In physics, it's a living, breathing rate or relationship. You have to insist on cause and effect. Don't just list a bunch of isolated facts for the examiner. Explain exactly why that line curves the way it does. Whether you're dealing with volume, density, fields, or particles, always anchor your interpretation in physical reality.
Okay, Section 4, real-world applications, where you use it.
Because physics isn't just some abstract concept that lives on a whiteboard. It's literally the operating system of our physical world.
Ideas stemming from measuring volume and density are everywhere, and for the exam, you need to be able to name at least one real situation where this stuff matters. Picture engineering and safety. Engineers have to calculate the density of building materials just to make sure a bridge can even support its own weight. Or transport, designing massive steel ships that displace the exact right volume of water to somehow stay afloat. It even applies to astronomy. Get this, the planet Saturn has a density so incredibly low that if you could somehow find a bathtub big enough, the entire planet would actually float in water. Understanding these concepts is how we predict and improve outcomes in pretty much every field out there.
Now for Section 5, Surviving Exam Traps, the Formula Trap. Because knowing the physics is only half the battle, right? Clearly communicating it to the examiner is the other half.
A super common weakness we see all the time is what we call the formula trap. Picture this. You get a question, you write down the correct formula, and then you just stop. That's a weak answer. Quoting an isolated formula without actually explaining the underlying variables and their physical effects is a guaranteed way to bleed marks. A strong answer? It uses our DREMA method. It defines the variables, explains the relationship, and links that specific formula to actual physical effects happening in the real world.
But wait, there is another major trap, the process trap. Simply tossing out a real-world example just isn't enough to get full credit. A truly strong answer requires you to explicitly show why your example follows from the physics principles. You've got to clearly justify the cause and effect link. For instance, if you mention that hot air balloons rise because of density, you have to explain the physics of why a change in volume due to heat actually changes the density, which then causes the balloon to displace the heavier, colder air. Cause and effect is everything here.
Finally, Section 6, Quick Recall, Securing Your Knowledge. To wrap up this explainer, we're going to run through 4 essential revision prompts. This is how you prove to yourself that the knowledge is actually locked in.
Whenever you finish studying a microtopic, like volume and density, I want you to ask yourself these 4 questions aloud. 1. What is the core idea? 2. What changes physically in the system? 3. What quantity, equation, or graph shows this relationship? And 4. Where is it used in the real world? If you can answer these 4 exact prompts verbally, entirely from memory without peeking at your notes, then your understanding is secure. You're ready to confidently tackle any short answer or structured question an examiner throws your way.
So I'll leave you with this final challenge. Can you define the key idea of volume and density? Can you explain the cause and effect chain without just robotically listing a formula? And can you justify one real-life practical use for it? Try to answer that out loud right now. If you can't quite do it yet, well, you aren't quite ready for the exam. But if you master cause and effect and diligently apply that DREA method, you won't just be memorizing physics. You will absolutely command it.